Now, I'd like to digress a little bit before we go on and we continue with our study of rings to talk about this adjoint notation. So on the previous slide, I talked about polynomial rings, and I wrote that as f adjoin x. And what I'd like to do is make sure that we're really clear on what the definition of it is when I take a set f and I adjoin an element alpha. So very formally, if I take a set f and I have an element alpha, I'm going to define f adjoined alpha as the set of a naught plus a1 times alpha plus a2 alpha squared, and so on and so forth, up through an alpha to the nth power, where all of the different a sub i's are elements of the set f, and n is some sort of natural number. And you want to note that I do want to allow for n to be any natural number. So I want to consider when n isn't there at all, when n is raised to the first power, up through when n is the 107th power. Really want to consider all those different possibilities. However, this is the very formal definition, but this probably isn't the best way to think about what f adjoined alpha is. You should really think about the set f adjoined alpha as the smallest set that contains all possible linear combinations of any arbitrary member of f and any arbitrary power of the element alpha. Or in other words, perhaps even less formally than that, let's say, suppose we started with the set f. Perhaps it was a ring, as it was for all of our previous examples, integers mod n, real numbers, and so on. And alpha is some sort of other element that we have, just an individual element on its own. And what we really want to do is we want to build a new ring, that the smallest ring we possibly can, that contains this new element and all of the old elements of our previous ring. What would we have to do in order to build a ring out of that? Well, we would have to take all positive powers of this element alpha, because we need our set to be closed under multiplication. I don't have to consider any negative powers because I'm not concerned with multiplicative inverses. That's not a requirement for rings. But anytime I pick elements of my new ring, I need to be able to combine them, either via addition or via multiplication. And so what I really need to do is I need to consider all these different powers of the element alpha, and then all of the different ways that I could combine those powers of alpha, either by multiplication or by addition, with the elements of f that I already have. And so this is what leads us into this definition of the set f adjoined alpha. And as on the previous page, the most familiar example of a set f adjoined alpha is a polynomial ring. So where we take something like the real numbers, and then we want to adjoin symbolically this element x in order to get polynomials. The set, if I started with the ring R, and I just wanted to add on this element that I call x, and form a ring out of all possible combinations of those things, then what I would be getting is the polynomial ring R adjoined x. Some less familiar examples, but things that we've seen so far, either previously in abstract algebra or last semester in abstract algebra. You should have seen the Gaussian integers, which we write as z adjoin I, and you should have seen the rational numbers where you take and adjoin the square root of 2. Another reason I want to talk about this adjoint notation is that there can be some confusion when you switch from something like polynomial rings to something like the Gaussian integers or the rationals adjoin root 2. For example, I think if you have seen me define it before, or perhaps this is the way that it's even defined in the abstract algebra textbook, if you take and you look at q adjoin root 2, the way that that's going to be defined in the textbook is a plus b root 2, where we require that a and b be rational numbers. However, this is not the same as the formal definition of f adjoined alpha that I listed on the previous page. So if we are thinking of square root of 2 as the alpha figure here, I've only listed a plus b alpha raised to the first power. I haven't considered what happens if alpha is squared or if alpha is cubed, and so on and so forth. Now, the reason that I haven't done that, so this differs from the formal definition on the previous slide, but the reason that I haven't done that is, let's see what would have happened if I would have taken and considered something like a plus b root 2 plus c root 2 squared. When I take that root 2 and I square it, I'm getting the number 2, which happens to be a rational number. So the next term in that sort of expansion, that c root 2 squared, is really just 2c. 2c is a rational number, a is a rational number, and I could combine the a and the 2c together to give myself just a different rational number. And since I'm considering the set of all possibilities where a and b are rational numbers, I'm going to have taken into account a plus b root 2 plus c root 2 squared already when I just take into account a plus b root 2. And similarly, hopefully you can convince yourself, if you went even further and you looked at something like d root 2 cubed, when you take that root 2, you cube it, you're going to get 2 root 2, and that can be combined with this b root 2 in order to get something of the form that we have listed here. So this is a different formal definition of q adjoined root 2, but it's a little bit simpler to wrap your head around, and it's still technically correct, even though it doesn't follow the pattern that we saw on the previous page. Now, just as an exercise for you to maybe get you understanding this adjoint notation even better, I'd like it if you could find an example of a structure or a set F and an element alpha, where it would also be correct to define F adjoined alpha as the set of things of the form a plus b alpha plus c alpha squared, where a, b, and c are elements of whatever set F you choose, and where you really and truly need exactly these three terms. So you could be kind of sly about it and say, I've already discussed an example where this works. Q adjoined root 2 happens to do this, but we don't really need that c alpha squared term in the Q adjoined root 2 example that we have on this slide. So it would be nice if you could come up with an example where you need each and every one of these terms, a plus b alpha plus c alpha squared, but you don't need anything more.